So let me start. Hello everyone. Welcome. This is the second talk of our seminar series, Stringy Seminars. And today's talk is by Arpit. He's a postdoc at University of Edinburgh. And today he's going to talk about generalized global symmetries in 2D CFTs. Let's welcome Arpit and yeah, Arpit, welcome to the seminar series, and yeah, you can start now.
Thank you, Bhaskar, for giving me this opportunity, and thanks everyone for joining in. My talk will be basically based on some recent developments in our notion of symmetries. And though I am using the word recent, but it has been going on for like about 12, 13 years now in its current formalism. So we're going to discuss something called generalized global symmetries and try to see some of its applications in various QFTs and specifically in 2D CFTs as we go along. And this is based on a couple of works that came out in 2 years ago with these wonderful set of collaborators, Javier, Pablo, and Herman, and also an upcoming work which we are trying to finish quite soon. So without further ado, let's get started. So we know that since the time of Noether, that whenever we have some symmetries in our system, then they imply conservation laws. Okay, and throughout my talk, I'll be focusing on global symmetries, and so essentially gauge symmetries, which are not global symmetries, where your symmetry parameter is not dependent on space and time. So those are what I'm calling as global symmetries. But gauge symmetries, as you know, they essentially mediate local interactions. They depend on your space-time variables. So we won't talk about those symmetries. So these are purely global symmetries. And like in 2014, about 12 years ago, as I said, there have been some reformulation of this statement by Noether, that, and we will see that whenever there will be some global symmetries in our system, it will always be the case that we will be able to find some operators that are associated with these symmetries. And furthermore, these operators will be topological. In what sense these are topological, how are they conserved, is what we will try to learn in this talk. So the slogan that I want to highlight is that if you have global symmetries in your theory with some conserved charges, so that's Noether's statement that we know since Noether, then we will always be able to say that there is some underlying operators which are topological, and that furthermore commutes with your Hamiltonian. And this commuting with your Hamiltonian is what brings in the nature of it being a global symmetry. Okay. So in order to set the stage, let us review some ordinary, very familiar symmetries. So let's say you have some QFT where you have one index current that is conserved. So it's a E1 current. So as you know, the conservation equation is just del mu J mu is 0. And if you are familiar with differential forms, then you will write it as D star J is 0. In component form is just the divergence less of the current. Now, one might ask that what does this current counts? Okay, so what are the conserved quantities for this current? And we find these conserved quantities, as you know, by integrating the temporal component of this current over, let's say, your whole 3 space. So you define Q as integration of star J, which in components is just the temporal component of the current, over the whole 3 spatial manifold. So when you do that, you get the conserved charge. So this is basic QFT exercise. And then you can exponentiate this charge. So you obtain the charge by a codimension 1 integration, and then you exponentiate it, and that gives rise to a unitary operator. So in this case, it's just e to the power I alpha q, and that unitary operator essentially acts on local operators in your Hilbert space. Okay, so you'll have some Hilbert space in some time slice. So imagine this square is my time slice on the right diagram, and these yellow lines are my particle wall lines. And when I'm integrating it over a time slice, which is like a codimension 1 or 3-dimensional spatial volume, then you catch all the particles that are there. Okay. So because particles don't end in time, because they're extended in time, if you do an integration over a codimension one time slice, then you catch all the particles that are there in this room. And so that's essentially that picture. And this is my expanded picture of that same codimension one volume, and these yellow dots are my particles. So again, this is usual symmetry that we know, but I am just calling it in a fancy way. And this fancy way of calling this new notion is what is called a zero form symmetry. Okay. So where does this zero comes from? This zero comes from the fact that the unitaries that you constructed act on local operators or zero dimensional objects. Okay. So hence the nomenclature zero form. Okay. Another thing, if you have any questions, then do please stop me at any point in the talk. Okay. Now let's try to generalize this idea. So let's look at another example actually. So let's look at ordinary quantum mechanics, where you know that the unitaries are something that act on a Hilbert space. And let's take this Hilbert space to be defined on a time slice, just T. Okay. Now we know that these unitaries, they remain invariant of time. So ut is ut prime. In this sense, we will call that these unitaries are topological. Okay. So irrespective of whatever time slice you choose, they remain the same. Okay. We will say more about it later. Furthermore, how do these unitaries act? So these unitaries, they act on local operators by what is called a conjugation action. Okay. So O is a local operator. The unitary acts like U, O, U dagger or U inverse, and it gives you something like O prime. Again, this is something you all are familiar with. Why do we impose this action? Because that's what preserves the norm. Okay, the norm of the wave function gets preserved if your operators act like this. Okay. Now, however, in the most general scenario, you may not be able to decompose, your space time into three space direction, one time direction. So you may not have a preferred spatial slice. So in those cases, such a conjugation action should be interpreted as a equation written inside some correlation function, and not just like an equation like this. Okay, so it's kind of an operator equation which is true wherever you put it inside some correlator. Okay. So in that sense, the topological nature will just be u of sigma d minus 1, the same as u of sigma prime d minus 1. And if you are lucky and find a time slice, then this is like ut is ut prime. Okay. And where topological means that if you have a time slice sigma d minus 1 and a time slice sigma prime d minus 1, then you can smoothly deform one to the other. And whenever you can do that, these operators will be independent of wherever you define them. Okay, so that's the picture I want you to have in mind. And furthermore, as you know that all these unitaries, by definition, since they are unitary and they will form a group, so whenever you will have a u, you will also have a u inverse, so that when you compose them, you just get the trivial operator or the identity operator. Okay. And you can denote this u prime as u inverse. Again, this is all that we know from ordinary quantum mechanics. I'm just trying to phrase it in a way that can be easily generalized. Okay. So whatever I'm calling topological, and these things for you are like they commute with the Hamiltonian, and hence their time translational invariant and such things. I'm just trying to present it in a way that will generalize to what to the notions that we will see quite soon. Okay. Okay. So now, yeah, so now let's talk about, if you don't have a preferred time slice, then how does this action look like there, this conjugation action? So what you can do is you can take the u prime, which was inverse, from the left and take it to the right side. Okay. So u o gives you o prime u. Okay. I have just taken the u inverse, multiplied it both sides, and written this equation down. And if you take t minus t prime to 0, this exactly reproduces the conjugation action which we saw. However, now written in this way, we will see that this conjugation action can be nicely understood in a very geometric picture. And the picture that I want to convey to you is what is called action by linking. Okay. So let's try to understand what this linking idea is. So now let's focus on this diagram. So on my vertical axis, I have time. On my horizontal axis, I have space, and I am suppressing all the spatial directions to just denote it by just one spatial axis. So this point y is where my local operator is sitting, local operator O, and I have a u, and then there is a u inverse. Okay, and these orientations are reversed to denote that one is u and another is u inverse. Okay, and because conjugation is like u o u inverse, this is how we will draw it. Now note that I said all of these unitaries, they are independent of any time slice that you pick, because as you know, they commute with the Hamiltonian. In our language, we will call that these operators will be immune to any smooth deformations that happen, or they are topological. So you can smoothly deform them. That's what gives rise to this second picture. So I can smoothly deform this upper operator and this lower operator, and I can make something like this. Now I can further deform this and get rid of these tails, and because they are u and u inverse, they nicely cancel off. So what I end up with is a nice circle or a sphere, if you like, defined on a d minus 1 manifold. So that's the idea, that you have u sphere d minus 1 or d minus 1 sphere acting on the operator O, and that gives you O prime. Okay, so this whole conjugation action can be reduced to a unitary which is defined on a sphere that wraps this local operator, and then you can topologically deform that sphere, and as you hit the local operator, you pick up O prime, and then you can trivially vanish away the remaining part of the sphere to get O prime. Okay, so this is a nice way to phrase this action of these operators, these unitary operators on your local fields in your Hilbert space, where I am rewriting the conjugation action in terms of what I am calling as action by linking. And the idea is this sphere links with these points. Okay. However, now imagine if instead of a d minus 1 sphere, I would have tried to do this with a d minus 2 sphere. Okay, so imagine in 4D, I take a circle, and then I'm trying to have a point, and then I want to do this kind of an action. Because everything is topological, you can essentially take this circle outside of the plane that the point is in, and they can shrink it to 0 without hitting the point. Because a circle and a point are not linked in three-dimensional space or 4D. However, a sphere and a point are linked. Okay, so this is why, without even looking into the dynamics or particulars of the theory, just by looking at what kind of extended objects are there in your theory, and if you can associate some symmetries to these operators or objects, you can already talk about what kind of linking will happen or not, and what kind of global symmetries will be there in your theory. Okay, we will see this more a little bit later, but that's the idea to why we write the conjugation action in terms of this linking. Okay, so what we learned from this exercise, where we were recasting everything that we know beforehand in terms of this fancy language, is that a zero form global symmetry is essentially a codimension one operator u, which is the unity that we are fond of, but now it is topological, it is invertible, and it acts via linking on your zero dimensional local operators. So now let's generalize all these ideas, and we will see that this language is powerful to easily generalize these ideas. So instead of a one index current, now let's focus on a two index current. So you have divergence less of a current, which has two indices. And again, in forms language, you will just write it as d star j is 0. Okay. Now, right away, let's try to see an example where such a thing exists. So in free Maxwell, you know that if you take the Hodge dual of the field strength in 4D, free Maxwell in 4D, then by Bianchi identity, you know that del mu epsilon mu nu rho sigma f rho sigma is 0. Okay, that's what we call the Bianchi identity. And we will see more it in this language, but let's ask what this extra index does. Okay, and what is the associated conserved quantity for this two index current. Now because you have an extra index, so imagine like these are strings. Okay, these are not point particles, but these conserved things are like strings. So because these are one dimensional extended objects in 4D, in order to catch all the strings in the room, you don't need to integrate over the three space. You can do a cross-sectional integration, okay? Transverse to the direction in which the strings are pointing. If you take a cross section, then you'll be able to catch all the strings. Okay, so that's what this diagram is showing. So instead of doing a 3D integration, you can do a 2D integration and you can catch all the strings. Okay. So that brings us to the charge that is associated. So you do a codimension 2 integration of the tempo of the star j of this current, and that gives you a codimension 2 operator now u, and you define the charge in exactly the same way, and the operator is just exponentiation of the charge. But the crucial thing is this charge is now done by integrating a codimension 2 surface. Okay, so this
Is it only for like fundamental strings or also for like emergent like QCD strings, etc., like emergent strings like which are approximate strings?
what do you mean by approximate string? Sorry.
Like in QCD, there are like confining strings which are not fundamental strings but emergent strings, which in high energy they are actually particles. They are made up of gluons. Those are like approximate emergent. Like
yeah, so I guess you can make this procedure work there, but in that case, it will be some approximate symmetries or emergent symmetries, but not like true symmetries across the RG. So there might be some length scale where this symmetry will pop out. Yeah.
Okay.
Right. So in this example that we saw of free Maxwell, so we know that, as I said, due to Bianchi identity, we have such a conservation. And now if you go back to high school physics, why do we have the Bianchi identity? That essentially captures the Gauss law for magnetostatics, which says that there are no monopoles. Okay. So this means these things that we are counting are essentially magnetic field lines. Okay. So the symmetry associated to the conservation of magnetic flux or the count of magnetic field lines is what is this one form symmetry in U1. Okay, the U1 electrodynamic free Maxwell theory that we discussed. So this superscript 1 is essentially saying that we have a one form symmetry. Now there is something really nice that happens with higher form symmetries, which is very contrast to what happens with zero form symmetries, is that for one and above form symmetries, the group that you get when you compose such operators is always an abelian group. Unlike in the zero form case, as you know, you can have non-abelian symmetries also. And the way to understand this is very simple. And we will see here that this linking will play a role. So imagine this is my charged object on which this codimension 1 operators are acting. So the blue box is one operator and the orange box is one operator. Now, in the top of the picture, they are in this order. But now, because I have an extra dimension to work with, and these are d minus 2 surfaces, so I can swap past one across the other and I can reverse their order without having any non-trivial intersection between the two. Okay. But this you could not have done for a d minus 1 operator or for a zero form symmetry, because those will be cubes in this picture. They will not be squares. So if you try to exchange cubes, then you will find some non-trivial intersection, because of which you have the ordering and you have non-abelianity for zero form or usual symmetries. But for higher form symmetries, whenever you have a group-like structure, you will always have an abelian group. So that means the only continuous group that you will have is U1, and all other cases of higher form symmetries will be discrete symmetries like Z2, Z3 and these things, okay? Because the only abelian continuous group is U1. Okay? So it's, in some sense, it's even simpler. And as we discussed in free Maxwell, if you further don't allow for electric charges, as we will see in the next slide, you will also have a U1 one form symmetry associated to electric charges. Okay, just like for the magnetic case. So let's try to understand that a bit more. So you know that if you are in free Maxwell, but if you allow for electric charges, then the only conservation that you have from Bianchi is this. But further, if you don't have electric charges, then the equation of motion also gives you another object, this, where this 2 index current is just the field strength F. So you will have an equation for F and for star F. So star F does magnetic flux conservation, but if there are no electric charges, then F does electric flux conservation, as you know. Okay. from Gauss law. Now, the objects that are charged under these extended operators or these one-form symmetries are what are called Tooft lines for the magnetic case and Wilson lines for the electric case. And many of you will be familiar with these objects. And as soon as you have some electric charges in your theory, then say this curly C is my Wilson line. So, and this orange dot is my electric charge. So if you have an electric charge, you can end this Wilson line on that charge. Okay, because this orange dot will source this Wilson line. Now you try to take this d minus 2 circle and try to link it. So before, when this charge was not present, this was an infinitely extended Wilson line. So you could always link this circle with this line because of the infinite extension of the line. But now, because it ends on a charge and things are topological, so you can just take it down and then vanish it away, and there will be no linking. And because there is no linking, there is no action on operators, so there is no U1 electric flux conservation when you have electric charge. Okay, again, this is something that you already know. I'm just phrasing it in this linking or topological language, but the idea is this. So that's why whenever you have Maxwell, whether electric charges are present or not, you will always have the magnetic flux conservation. The Wilson line symmetry will only appear when you don't have electric charges. Okay. Then let's talk a bit about the importance of antisymmetric forms or differential forms in this picture. So I was always able to write down a differential form equation for these symmetric operators. But crucially, I was using one feature, and that feature was exactly this thing, that whenever I wrote down this conservation, these indices, they were antisymmetric. Okay. And why did I take it? Now let me clarify that. Because you could also try to say that I have something called a stress tensor in my theory, and that is also conserved, and it's a 2-index operator. So does it fall under this classification? And the answer is no. Why? Let's try to understand. Yeah, so as I said, we have always been taking antisymmetric indices for our currents and not symmetric indices. And the reason is we were talking about two kind of things. So one is the topological nature of these operators, and another is something to do with global symmetries. But now recall that how do you define a stress tensor in your theory? In some way, you always define a stress tensor by coupling it in the action by the help of a metric. Okay, so if you have a metric in your theory, then that helps you to write down a term in your action which involves the stress tensor. But a metric is a local degree of freedom. Okay, so it's not topological. So anything that couples to the metric is always a local quantity. So the stress tensor is a local quantity. Furthermore, if you are familiar with Chern-Simons theories, so you would recall that you could write down Chern-Simons action without the need of a metric. So you just write A wedge, dA. Okay, and no metric is involved. But in Maxwell, let's say you are writing the kinetic term, then you write F wedge star F. So the star F, the Hodge duality brings in the metric. So that's why differential forms are the usual language to write down topological operators, topological objects in the action, and they don't couple to the metric. So this is the reason why we only talk about antisymmetric or differential forms in this picture, because first we are dealing with global symmetries, and second we want them to be topological or impervious to any smooth deformations. Okay. And there is also a famous no-go theorem by Coleman and Mandula, and that says that in any QFT for 2 dimensions and higher, whenever you have such higher index currents, which are also known as higher spin currents, the S matrix is always trivial. So the theory is a theory of only free particles. So and we want to do something interesting, have some interaction in our theory. So that's another motivation why not to care about symmetric currents or generalization of the stress tensor. Okay. So let's now move on to some concrete examples of QFTs where these appear. So let's now take again QED, but now let's also couple the QED to some massless Dirac fermions. Okay, so psi and psi bar are my massless fermions, massless Dirac fermions, and we will right away see why I am considering such configurations. So let's first ask what are the symmetries of this theory. So we have a gauge symmetry, which is the vector symmetry. associated to the vector phase rotations psi bar gamma mu psi. But since this is a gauge symmetry, we won't care about it. It's not a true symmetry of our theory. It's just a redundant description. We also discussed this one form global symmetry, which is the Hodge dual of the field strength, and it is conserved by the Bianchi identity. And if you recall from your electrodynamics course, then you can write down the magnetic and electric field as some components of this Hodge dual of the field strength. Furthermore, if you know, then there is also an axial symmetry at a classical level, which is related to the axial phase rotations, psi bar gamma mu, gamma 5 psi. And this is precisely the case when your fermions are massless. So because if you have a mass term, then this symmetry is classically explicitly broken. But if you don't have the mass term, then this is conserved. However, there is a funny thing that happens is if you take this symmetry and you quantize your theory, then you get what is called a quantum anomaly or a APJ anomaly. And what does this anomaly say? Is that the non-conservation of this current is given by the field strength F wedge F. Okay. But we have been defining the Hodge dual of this field strength as this 2 index current. So you can write down the anomaly equation as D star J as star J with star J. Okay. So what for people who are not familiar with anomalies, let me tell you very briefly what these are. So it is essentially what happens is you have a symmetry at a classical level. This equation del mu j mu is 0. But when you quantize your theory by doing a path integral, you find that everything goes through except that the path integral measure is no more invariant under these axial phase rotations. Okay. So when you do psi to e to the power I alpha gamma 5 psi, so this gamma 5 takes care of the axial rotations, you see that the path integral measure, it fails to be invariant. And that invariance is picked up as the non-conservation of this axial current. Okay. So a symmetry at a classical level no longer remains to be true at a quantum level. Okay. And so that's what an anomaly normally is. But now in this one form language, we are trying to see that this anomaly can also be recasted with the help of this one form current. Okay. And at times people denote this anomaly with a triangle diagram. So if you compute a triangle diagram of del mu, j mu with and two other current insertions, then this is where the anomaly appears at one loop level. And we will briefly touch upon it a bit more in next slides. So any questions till now at the moment?
Yeah, just a query, like when you talked about anomaly, what's like the physical interpretation of this? Like classically there is symmetry, but in quantum, when you're quantized, it's not. So what does it like physically manifest into?
So one thing it physically manifests is that normally when you have a global symmetry, you can always talk about how to gauge it. Okay, so we all do this all the time, and like you take this derivative operator and you associate a gauge field to that, and you get this covariant kind of derivative, and you write down your QED Lagrangian in terms of this new derivative. So you do this gauging procedure. But if this symmetry fails at the quantum level, then the first thing is you cannot gauge such a symmetry. So it leads to some obstruction in gauging. So that's one physical thing that happens, that you symmetries that are anomalous, you cannot gauge them. So people rephrase these anomalies as saying that there is some obstruction to the gauging procedure. Second thing that happens is, so what happens is when you do not have an anomaly, then you will have in your spectrum some kind of a gap. Okay, what do I mean by that? So it means that you know that in QFT there is a unique ground state. Okay, and the first excited state that appears in normal ordinary QFTs is after some gap. Okay, so this is the gap that people keep talking about. However, if you have only anomalies in your theories, then this gap that disappears. Okay, so either you will have what you already know as the spontaneous symmetry breaking, where you will have a degenerate set of vacua, or you will just have gapless modes in your spectrum. Okay, so there will be no trivially gapped, which is this vacuum that I'm talking about, phase in your IR. So if you do a RG flow in your IR, there will be no trivially gapped phase or no unique vacuum, and there will only be massless modes. Okay, so this kind of a picture is more like coming from a condensed matter point of view. So in condensed matter, when people say anomalies, they say that there are no trivially gapped phase in your IR. Okay, but high energy theorists like to say it that you cannot gauge the symmetry that you are looking at. And there is even another interpretation which I like to think, and I think this is very much intuitive, is before we quantize our theory, and when we are just at the classical level, we talk about the phase space. Okay, but in phase space, everything is just fields or functions. There are no operators there. Okay, so your functions, they act on some local fields, and that's how you carry out your calculation. But when you quantize your theory, then essentially the phase space quantization tells you that you dress all of these local fields as some operators where they live on some Hilbert space now. So the action that was there on the phase space variables now translates into where these operators act on some states in your Hilbert space. Okay. But now note that states in your Hilbert space are identified up to a complex phase. Two different states with one imaginary phase are essentially the same because they give rise to the same norm. But this was not there in the classical picture. If two fields were distinguished, means they are distinguished. But in the quantum picture, there can be a phase difference, but they are essentially the same. So at times, when these operators act on such states where there is a phase difference, it actually really imprints itself on the Hilbert space. Like you'll be able to measure this phase difference. That imprint is what is captured by the anomaly. People sometimes mention that there is something called a central extension. So maybe if you are familiar with CFTs, then you will know that conformal algebra is what is given by the Wheat algebra. But then when you quantize the algebra, you get something called a Virasoro algebra, and they differ by a central term. Okay. So that central term essentially captures this phase, this complex phase, when you quantize your theory, which in many cases is trivial and doesn't matter. But when there are symmetries that give rise to anomalies, there is a way to pick out this phase, which in CFT is the central charge. So yeah, so that's more like another physical imprint of these anomalies. Okay.
Yeah. Okay.
Thank,
Thank
thank
you.
you for
Thank
that. Now, moving on to some applications. So, we know that the photon is massless, and we know the textbook reason is that you have a gauge symmetry, you ungauge symmetry, and you will not be able to write down a gauge invariant mass term for the photon in your action. However, we now also understand that there is a global symmetry point of view for the masslessness of the photon, and that comes from like a Goldstone theorem, but a Goldstone theorem for extended symmetries like this one-form symmetry. So we discussed that there is this magnetic one-form symmetry. So because it's also in the truest sense of symmetry, you can write down its phases. So a Goldstone theorem for this, and it was done by Iqbal, Nabil Iqbal, and Iñaki Echeverria and Diego Hoffman and company, and they found that if you do a spontaneous symmetry breaking of this one form symmetry, the Goldstone that you get is indeed the photon. And the way this calculation is done is you take this Hodge dual, you act it on your vacuum, and then you take its overlap with a photon state. Okay, so A dagger is my photon excitation, my one photon excitation, and then in some gauge, let's say Feynman gauge, you compute this computation. And actually, interestingly, Tong in his notes, lecture notes of gauge theory, he does this computation, and then you will find that the overlap is non-zero. So you pick out the photon Goldstone, and now you have a more better understanding of why the photon is massless, because you have a robust symmetry principle guiding it, which is this spontaneous symmetry breaking of the one-form symmetry. And the photon is precisely the Goldstone boson for this state. Now, also we looked at these anomalies, and we said that we could recast them using these one-form symmetry operators.
In the
However,
case of abelian Higgs, how does like it change? Like in that case, the photon is massive, right? The abelian Higgs mechanism.
yes.
What happens to the magnetic one-form symmetry in that case?
So in that case, either you will explicitly break that symmetry, or you will have some like yeah. So or the symmetry will be unbroken. Let's say. So if this, so one case is the symmetry is not just not there, or in other case the symmetry is there but it's like confining. So if you
Okay.
have yeah, so just like in QCD you have these confining phases, so where the underlying symmetry is unbroken, you develop these flux tubes. Okay, your forces, they become short ranged. So in that case
Mm.
the photon will be probing short range interactions, not like
Okay.
long range in QED where it is infinitely extended. Yeah. So, yeah. So coming back to the anomaly point. So recently people realized, like 3 years ago, by this nice paper by Choi Lam Shao, that this anomaly can be understood as some non-invertible global symmetry. Okay. So let me explain a bit more what this non-invertibility means. And then in the remaining of my talk, that will be kind of playing the main role. So we will see more of it later. But for now, what these people were able to show is that we discussed that classically for any real angle alpha 5 there was a axial phase rotations, but these people showed that when you have this anomaly at the quantum level, only for rational angles of alpha you do get some topological operators that commute with the Hamiltonian. Okay, so you don't get the conservation of the axial current, so that's still true. There is no axial current that is conserved. However, you can construct some topological operators that commutes with the Hamiltonian, but they remain topological only for some rational angles. Okay, where there is this axial phase rotations. So because of these rational angles criteria, you don't have an inverse for all such operators. Okay, there will be some operators which will have an inverse, and there will be some that won't have an inverse. Okay, and this is what people started calling as a non-invertible symmetry. And this should be contrasted with when the case there is an explicitly broken symmetry. So let's say if you don't have even at the classical level a symmetry like that, but the vacuum of that theory will be different from this theory where you have these non-trivial non-invertible topological operators. Okay, and as we will see, having these non-invertible operators is actually good in the sense that they will be able to constrain your spectrum in some ways, or they will be able to dictate because they will be preserved along the RG flow just like any other symmetries. So they'll be able to constrain your theories and they will be powerful. Okay, so yeah, we'll talk more about this non-invertible things. Let me actually, for interest of time, skip this slide. So this is some work that we did in effective field theory with these non-invertible symmetries. But if you're interested, I can come back to it after the talk. But let me skip that. So let's directly go to non-invertible symmetries. Okay. So consider operators LA and LB so that they compose in such a way that you get an addition of operators on the right hand side. So not just one single operator, which is what would have been in a group like case. So if you compose two group elements, you get just one group element, but now you get some kind of a direct sum or like a string of group elements. So when that is the case, then what is called that this L is what is called a non-invertible symmetries, in the sense that it doesn't form a group. Okay, not all of these L's will have inverse. In the precise mathematical setting, this is what is called a semi-ring. Okay, but for us, it's just any operator that satisfies such a composition. Now, so even if they are such exotic operators that they do not have inverses, they still can be topological and they still may commute with the Hamiltonian and hence can give rise to some conserved charges. Okay. So even though no conserved current might exist, you can still have some way to describe their action. Okay. And write down some interesting things with them. And we discussed very briefly that the 4D ABJ anomaly is one such example where these operators that are associated to axial phase rotations, they are topological, they commute with the Hamiltonian, but since they are only defined for rational angles, they are not invertible. There is a nice playground, the playground of 2D conformal field theories. I will slowly explain what 2D conformal field theory is. But in this playground, there are infinitely many examples of these non-invertible symmetries, and they were known since the 80s after the work of Verlinde, but nobody really thought of them as symmetries. Okay, and famously they are called Verlinde lines. So we will focus on a subset of those 2D CFTs, what are called rational CFTs. Again, I'll explain what these terms are. And yeah, we will see that you can write down the partition function of a CFT in terms of characters and these kind of things later. Okay. So let me give you a quick recap of conformal field theory. So you know that the relativistic invariance of QFTs tell us that we should have Poincare symmetry in our theory. So if on top of Poincare symmetry or relativistic invariance, you impose what is called scaling symmetry and something that's called a special conformal transformation, then you get what is called a conformal symmetry. Okay. And physically all it means is that your theory will be invariant under those coordinate transformations that preserves the angle between intersecting curves. Okay. So whenever you have intersecting curves in your theories, you do some mapping and the angle remains the same, just like scaling. So if you scale up or scale down, the angles remains the same, then that will be called a conformally invariant or a conformal field theory. Okay. So it's a extra symmetry group on top of Poincare symmetry. Now, in two dimension, it turns out that these conformal symmetries are very special. In fact, in two dimension, any holomorphic function essentially is a conformal transformation. Okay, so so conformal transformation essentially becomes complex differentiable in two-dimensional CFTs. Sorry, in two dimensions, and that is why the conformal symmetry is infinite dimensional in 2D, because you can have infinite number of holomorphic functions, and the symmetry algebra is infinite dimensional, which is what is called the Virasoro algebra, as I was saying. So it has infinite generators. Furthermore, you can start with a plane which is a 2D, like a 2D plane, which is a 2D setting, and then you can do a conformal mapping to a cylinder. So imagine wrapping the two edges of a plane, and then further you can map the remaining open ends of the cylinder to form a torus. Okay, so this way you can start with a theory on a plane and end up with a torus. And but because you are on a torus, you should respect the diffeomorphisms of the torus. Your theory should be invariant under the diffeomorphisms of the torus. And these diffeomorphisms on the torus are what are captured by what is called the modular group. And this is why if you write down an action or a path integral on a torus, it should be modular invariant. Okay, so the partition function that you write down will be modular invariant. And this SL2Z is essentially the modular group that captures diffeomorphism on a torus. So you get these nice constraints that helps you to solve your two-dimensional CFT completely. Now, roughly when people talk about a CFT, they many a times mention what is called a CFT data, and that CFT data is what is captured by what's called the central charge. So imagine it's like some degree of freedom in your theory and some conformal weights. So what are these conformal weights? So you have some special fields in your theory called primary fields. Okay, they transform in a certain way under these conformal symmetries, and the operator that takes care of this scaling, under that they develop some eigenvalue. Okay, and that eigenvalue is precisely what is called the conformal weight. And then in CFT you have even something more powerful, is that you can bring two local operators close to each other, and you can write their composition as a sum of many local operators living at that point with some coefficients. Okay, those coefficients are what are called operator product expansion coefficients, or OPE coefficients. Okay, for instance, stress tensor is a local operator. You can write down stress tensor and maybe some U1 current. You can bring them together and write it as a chain of other local operators at that point. So once you know the central charge, the eigenvalues of the scaling operators, and the OPE coefficients, then in some sense you have every information about the 2D CFT that you want. Okay, and hence these are called the CFT data. Now, why study 2D CFT? Well, if you are into string theory, then the string wall sheet is a 2D CFT. From a condensed matter point of view, these are very relevant for critical systems in two dimensions, because as you might be knowing, when you are in a phase transition point, that phase transition point is exactly a CFT. So it's a conformal invariant fixed point. So if you want to understand, like, for even in a simpler sense, like how ice melts into water, or water evaporates into water vapor, then at those critical points there are CFTs. So you need to understand CFTs. Furthermore, if you are into holography, then in 2D holography, you have to do ADS3 CFT2. And if you are like me and want to do understand the mathematical aspects of CFTs, then there are nice mathematical structures ranging from representation theory to Lie algebras, vertex operator algebras, etc. in 2D CFTs. So for the remaining of my talk, we will focus on even a smaller subset of 2D CFTs, what are called rational CFTs. So what are rational CFTs? So I said that there are some special fields which I will denote as primary fields that have a very particular kind of scaling under the scaling operators. So if such primary fields are finite in your theory, then that essentially tells you, by this work by Greg Anderson and Greg Moore, that the central charge and the conformal or the eigen values of such operators are rational, and that's why the name rational CFTs. So they're a special class of 2D CFTs which just have a finite set of primary fields. So not only now you have solvability in your system due to conformal symmetry, you also have finiteness, okay, because you just have finite things to deal with. So there is something called primaries that we discussed, but you can write it purely in terms of the Lie algebra language. So you take so you construct your stress tensor and you decompose the stress tensor into some modes. So L0 and L0 bar are some zero modes of the stress tensor. So if you have a state in your Hilbert space such that its action produces some eigenvalue h, this h is what is called the conformal weight, and such a state will be called a primary state. And for any higher modes of the stress tensor, it will be annihilated. Okay. And these stress tensor modes, they satisfy the conformal algebra or the Virasoro algebra. And this C is what is called the central charge that I was denoting. And this is also the anomaly that appears in this 2D CFTs. Okay. So if you know a bit about the Weil anomaly, then you will, or the trace anomaly, then this C precisely appears there, and it captures this property of projectivity in your representation. So as I said, in your classical picture, you have a linear representation, but as soon as you go to the quantum picture, because things are identified up to a phase, you have a projective representation. So because of this projectiveness, this anomaly pops up at sometimes. And similarly for the anti-holomorphic sectors. Okay, so another feature of 2D CFTs is you can nicely decouple holomorphic and anti-holomorphic sectors, or what people call the left and right moving sectors. Okay. On top of conformal symmetry, you could also have some internal symmetries, like some internal group U1, SO2, SO3, and you will have some currents with respect to those groups also. So they will also satisfy another Lie algebra, and this is also called the current algebra or the Kakmuri algebra. And it's not very important for us, but what's important is this picture, because that reveals for us how the states are distributed in the Hilbert space of the theory. So on the leftmost part, I have the vacuum sitting at the bottom. So that's like my vacuum state in the Hilbert space, and I can act on it some higher modes of the stress tensor to generate excited states. And these excited states are what will be called descendants in my theory. Okay, so that's the term descendants. Similarly, you can have some other primary in your theory, not just the vacuum primary. So this is I am denoting as phi. And again, you can act your higher modes of the stress tensor on it and describe excited states in that family. So in this way, all the primaries, which essentially form for you the representations of the conformal algebra, they give rise to nice families where they themselves live and their descendants. Okay, so that's the structure of Hilbert space in your 2D CFT. And this is what is called the Verma module or the conformal family of states in your theory. And similarly for the anti-holomorphic parts, here I am just looking at the holomorphic sectors. So as I said, when you have finite primaries, then it's called rational CFTs. And as we discussed, that Virasoro conformal representations are what are called Virasoro primaries. They're in one-to-one correspondence. And the initial CFTs that were discovered by Belavin, Polyakov, and Jamoldo-Shikov. So if your central charge lies between 0 and 1, you always have a finite set of primaries. That's what they found. And this is called the minimal series, very important in condensed matter. The 2D Ising model is one such minimal model. But as soon as you have central charge greater than 1, then the number of representations become infinite. Okay. Taking use of this torus modular invariance, you can further write down this torus partition function in terms of what are called characters. So this partition function can be written in terms of holomorphic and anti-holomorphic blocks, which are called characters. And what these characters do, they essentially count how many descendants are there in one family. So this I denotes a family like the vacuum family or other conformal primary families, and they essentially counts for you how many descendant states you have at each excited level. Okay. For instance, and the reason is this, so let me tell you a bit more. So you see that at the second excited state, I can have L minus 2, okay, acting on the vacuum. Now let's go to the third excited state. So you could have L minus 3, or you could have L minus 1 times 3, or L minus 2, L minus 1. So you can write down 3 in different partitions of 3. So there are different ways you can have degeneracies in these states. So those degeneracies are essentially what is counted by these characters. Okay. So they represent how many descendant states you have at any level. And then there are some nice number theoretic results, but again, let's skip them and directly go to the meat of the talk, looking at some non-invertible symmetries. So for this, let's focus on a very particular example, the 2D Ising model. So the 2D Ising model has 3 primaries. Okay, one what is called the vacuum primary, denoted as 1. There's something called a energy primary, denoted as epsilon, and a spin primary, denoted as sigma. And the subscripts denote their conformal weights. One is just 0 conformal weights, then half and half for the energy, and 1/16 for the spin. Now it's known that for all of these primaries, they are in one-to-one correspondence with what are called Verlinder lines or extended operators. But what these operators do is what we will try to understand. So the identity line does nothing. As the name suggests, it's a trivial line. The eta line, it implements the spin flip symmetry of your Ising. Now you know that if you take your 2D Ising model Hamiltonian, then if you do, so that Hamiltonian enjoys a Z2 symmetry. Okay. That Z2 symmetry is essentially implemented by the extended operator that is in correspondence with this energy field. Okay. But this being a Z2 line, it is invertible, and this belongs to the Z2 group. However, there is a non-invertible line that comes when you look at the line associated to the spin field. Okay. And that line is denoted as capital N. And why it is non-invertible? If you write down the OPE coefficient expansion for the N line with itself, you get the identity family and also the Z2 family. And you clearly see that because it doesn't square up to identity, this is non-invertible. Okay. Because if you do the OPE for the Z2 line and the N line, then you will pick up N just like this. Okay, the N conformal family. Now imagine if N had an inverse, then you can hit it with an inverse, and you will just get that N inverse is eta. So 1 will be eta, but we know that eta is not 1. It is the non-trivial Z2 element. So this is because this tells us that N is not invertible. Okay. And what does this do in the physical sense is it implements what is called the Kramer-Swannier duality on the Ising model. Okay. So there is a Kramer-Swannier duality which essentially maps local operators to non-local or disorder operators in the 2D Ising picture. And this precise map of local to non-local is what brings in the non-invertibility. Okay. And you can then consider these extended operators, look at its actions on many primaries, and try to see how the non-invertibility creeps in there. And if you draw such a table where these are eigenvalues born out of the action of these operators on the primaries, and you precisely see that when this N operator acts on this spin field, it projects it to 0. So there is no way to invert this operator. Now I think I have like 5 minutes to be precise. So let me quickly say what we tried to do with these non-invertible symmetries in CFTs. So we wanted to study their entanglement properties, but let me tell you what kind of entanglement properties. So you know that in 2D CFTs, there is this nice result that dates back to Cardi and Calabrese, that any 2D CFT, the entanglement entropy of some interval of length L, the leading piece of that entanglement goes like the central charge of the theory times log of the interval length. Okay, maybe I have a formula to show that. Let's see. So
It's only for like the ground state, right? If I remember correctly.
yes, it's only for the ground state. Actually, I'll show it to you when we go there. But yeah, it's precisely for the ground state. Thanks for pointing out. But what we wanted to do is, suppose you have some internal symmetries on top of conformal symmetry, then your Hilbert space can decompose into irreps of that symmetry or charge sectors of that symmetry. Then you can ask that those different irreps, they could contribute some entanglement to this total entanglement formula of Cardi. Okay, because now your Hilbert space is decomposed into these irreps. So is there a way to understand how much entanglement is coming from each irrep? Okay, so for the group like case, this was studied under the name of what is called symmetry resolved entanglement entropy by a couple of people, Goldstein and Sella, about 7 years ago. Now we wanted to do it for those symmetries which are non-invertible, because if non-invertible symmetries are true symmetries, then you should be able to compute this quantity that captures entanglement from these irreps. But now instead of group like symmetries, if you have non-invertible symmetries. So when we did that, the result that we get, so let me show you what it looks like. So let's see. Yeah, so that is Cardi formula. So this boxed equation is what Cardi formula looks like. So the leading piece will still go like central charge, just like the Cardi result, because that's the universal piece that Cardi found out. But the next two leading piece, which is the first subleading piece, that goes like dimension of the irrep that you are zooming into over the cardinality of the group. So that is the group like result. So it goes like log of dimension of the irrep over the group. So if you have a Z2 group and you will have two irreps, even and odd, then this piece will look like log 1/2. So 1 is the dimension of the irrep, either the even or the odd irrep, and this is the cardinality 2. So this says that for Z2 symmetry, the entanglement contribution is equipartition between the even and the odd sector. We wanted to see what happens to this subleading term when you have non-invertible symmetries. Okay. One more clarification. So this epsilon is essentially the UV cutoff that you introduce to regulate the endpoints of your entangling surface. Okay. So in that epsilon cutoff, this next to leading piece is independent of it, because this is 1 over epsilon, this is constant, and again epsilon and so on in that expansion. Now, if you do this for the non-invertible symmetries, again, let's skip all of these situations. So what we end up getting is this boxed formula here. So the leading piece is again the same, which is central charge over 3. The subleading piece goes like dc square over mod c, where instead of irreps of group, now we have what is called quantum dimension of the line. So remember I introduced these Verlinde lines, so they were topological lines. So to each line you can associate what is called the quantum dimension. And what is that quantum dimension? It is simply, as I said, you can take these lines, act it on some primaries. Okay, so now imagine acting it on the vacuum primary and then computing the vacuum expectation value. So 0, this extended line, and 0. Okay, so that quantity is what is called the quantum dimension of the line. And it turns out that the second piece goes like quantum dimension square over the number of lines you have in your set. So like in Ising, we had 3 lines, so yeah, so it will be 1 over 3, let's say. Okay. However, now you have a feature that was not there before, and the feature is this. Now, there is a technical reason why this quantum dimension is actually greater than 1 for non-invertible line, but equal to 1 for invertible line. So let's say now you want to measure this quantity on some lattice. Okay, and because log of 1 is 0, so all invertible lines will just give you 0 at the subleading piece. So you won't be able to detect anything non-trivial when you do it on a lattice. But if you have a non-invertible line and try to measure this on a lattice, the hope is that you will find, because now log of something that's greater than 1 is non-zero, you will pick up some non-zero piece that's like an entanglement contribution into the Cardi formula, but at the subleading order. So this way, we hope that, if somebody would be able to compute this quantity on a lattice, you should be able to figure out a signature of invertibility, non-invertibility as this non-zero contribution piece on the lattice. But it's still something very far-fetched. So we've been talking with some people who are good at lattice to try and help constructing such operators on the lattice. Let me end this by saying why that is difficult. Because this whole 2D CFT program, only at the continuum limit, when you have exact conformal symmetry, these Verlander lines, they have nice non-invertible features and action. But when you are away from the continuum, then there is no nice picture of this non-invertibility. Very recently, some work by Seiberg and Shao have been to show how to write such non-invertible objects in terms of some translational operators on a lattice. So these are very early stages of doing this on a lattice, but okay, that's the hope. And now let me skip all over these things. And again, yeah, so yeah, I think let me end there. And sorry for going a bit over time, and if it was a bit rushed towards the end, but thanks for listening. And if you have any questions, do let me know.
Yeah. Okay. Thank you, Arpit, for such an informative talk. Now let me open the platform for any questions. If anyone has any final questions, please ask now. Okay, so if not, let's thank Arpit for the talk. And yeah, thank you everyone for attending. And let me also announce that the next talk will be on next to next Sunday, so after like 15 days. And yeah, and I also want to announce that we will be soon also starting a different seminar series called Chaotic Seminar Series, in which topics related to chaos will also be discussed. So those who are interested, please join. And again, thank you everyone, and thanks Arpit a lot for giving
Thanks.
this talk. Yeah, yeah, Shriman.
I just said thank you to Arpit.
Okay.
Thank you.
Okay. Thank you everyone for joining. Let's meet in the next seminar series. Thank you.